As you settle in and allow your breathing to slow, imagine a wide northern sky stretching gently above you. The air is crisp but calm, the horizon soft and open, and somewhere far above, faint ribbons of light begin to drift. Tonight, we begin a peaceful journey into the quiet science of auroras, also known as the northern and southern lights. These glowing curtains of color have fascinated travelers, scientists, artists, and storytellers for centuries, not because they are loud or dramatic, but because they appear silently, moving like slow thoughts across the sky. Welcome to this gentle exploration of aurora facts, designed to help you relax, unwind, and perhaps drift into sleep while learning something quietly beautiful about our planet and its place in the solar system. If you enjoy calm, educational journeys like this one, you're warmly invited to like and subscribe, but only if it feels right for you. And if you'd like, you can leave a comment sharing your country, your city, and the time you're listening from. Many people around the world listen to calming science at night, and it's comforting to imagine those quiet connections. Auroras are among Earth's most elegant natural wonders, blending space science, atmospheric physics, and geography into a single, slow-moving display. They are closely connected to the sun, even though they appear in the darkness of night. Every second, the sun releases a gentle stream of charged particles known as the solar wind. This flow travels across the vast distance between the sun and Earth, carrying energy, motion, and invisible electric charge through space. When these particles reach Earth, they encounter our planet's magnetic field, an invisible shield generated deep within Earth's core. This magnetic field protects our atmosphere and life on the surface, guiding many solar particles away. Some, however, are gently steered toward the polar regions, where the magnetic field lines dip closer to Earth. This is why auroras are most commonly seen near the Arctic and Antarctic, in places associated with quiet tourism, remote travel, and pristine natural landscapes. As solar particles descend toward Earth's upper atmosphere, they begin to interact with gases like oxygen and nitrogen. These encounters release energy in the form of light, much like a slow, natural version of a neon sign. Oxygen often produces green or red light, while nitrogen contributes blue or purple tones. The result is a soft, flowing glow that can stretch across hundreds of kilometers, yet remains almost completely silent. The most common aurora color is green, typically appearing around 100 to 150 kilometers above Earth's surface. Red auroras occur higher up, sometimes more than 200 kilometers above the ground, while blue and violet shades form lower in the atmosphere. These variations remind us that Earth's atmosphere is layered, structured, and dynamic, even when it feels still beneath our feet. Auroras are not limited to the northern hemisphere. In the south, they are known as Aurora Australis, or the Southern Lights. While fewer people see them due to geography and limited tourism infrastructure, they are just as beautiful. Travelers to places like southern New Zealand, Tasmania, and Antarctica occasionally witness these quiet displays, combining luxury, expedition travel with deep encounters in nature. The word aurora comes from Roman mythology. Aurora was the goddess of dawn, who renewed herself each morning and flew across the sky to announce the rising sun. The name is fitting, as auroras resemble a slow, luminous dawn unfolding in the darkness of night. The term Borealis refers to Boreas, the Greek god of the north wind, while Australis means southern. Long before modern science, cultures across the world developed their own interpretations of auroras. Indigenous Sami communities in northern Scandinavia viewed them with respect and caution, believing the lights carried messages or spirits. In parts of North America, some indigenous nations described auroras as the dances of ancestors. These cultural interpretations remind us that human curiosity has always blended observation with imagination, history with science. From a scientific perspective, auroras are closely tied to space weather. Changes in solar activity, such as solar flares or coronal mass ejections, can intensify auroral displays. During periods of high solar activity, auroras may appear farther from the poles. These rare events often spark global attention, photography, and increased interest in astronomy and atmospheric science. Modern technology allows scientists to study auroras using satellites, ground-based cameras, and magnetometers. These tools help researchers understand not only Earth's atmosphere, but also how solar energy interacts with planets throughout the solar system. Auroras have been observed on Jupiter, Saturn, Uranus, and Neptune, each shaped by different magnetic fields and atmospheric compositions. This makes aurora science an important part of planetary exploration and space education. Despite their scientific importance, auroras remain deeply calming to watch. Their slow movement, gentle colors, and unpredictable patterns naturally draw the mind into a relaxed state. Many people travel long distances, investing time and resources to witness them in person. Northern tourism economies in Iceland, Norway, Finland, Canada, and Alaska have grown around aurora viewing, blending science, education with sustainable travel experiences. Auroras remind us that Earth is not isolated. Our planet is connected to the sun through invisible forces, and to the wider universe through physics that operates quietly and constantly. Even when we are asleep, solar particles are flowing. Magnetic fields are guiding energy, and faint lights may be glowing far above snowy forests or frozen seas. As we continue this journey, we'll explore where auroras are most commonly seen, how they change with the seasons, and what they reveal about Earth's atmosphere and magnetic environment. Each fact will unfold slowly, like the lights themselves, connecting science, geography, history, and wonder in a way designed to soothe rather than rush. For now, allow your thoughts to drift like soft green arcs across a dark sky. There's no need to remember every detail. Simply let the ideas settle, knowing that the quiet science of the northern lights will continue to glow gently as we move forward. As we continue drifting gently beneath the idea of glowing skies, it helps to imagine Earth from far above, slowly turning in the darkness of space. From this peaceful distance, patterns begin to emerge. Auroras are not random decorations in the night sky. They follow geography, magnetism, and latitude with remarkable consistency, appearing most often in wide, invisible rings around the planet's magnetic poles. These rings are known as auroral ovals, They encircle the Arctic in the north and Antarctica in the south, forming zones where aurora activity is statistically most likely. Within these regions, the chances of seeing auroras are higher. The displays often brighter and the movements more complex. The auroral oval shifts slightly depending on solar activity, expanding during strong solar storms and contracting during quieter periods. In the northern hemisphere, the auroral oval passes over parts of northern Norway, Sweden, Finland, Iceland, Greenland, northern Canada, and Alaska. These regions have become well known in global travel and tourism for their dark winter skies, low light pollution, and wide open landscapes. Many travelers plan their journeys around aurora forecasts, blending science-based prediction with patient observation. Latitude plays a key role. Auroras are rarely visible near the equator because Earth's magnetic field directs charged solar particles toward the poles. The closer you are to the magnetic pole, the more directly these particles can enter the atmosphere. This is why cities like Tromsø in Norway or Fairbanks in Alaska are considered prime aurora destinations, offering both accessibility and consistent viewing conditions. However, auroras are not fixed to specific cities or landmarks. They are dynamic, constantly responding to changes in the solar wind and Earth's magnetic environment. On especially active nights, auroras may be seen much farther south than usual. Historical records describe auroras visible in southern Europe, the United States, China, and even near the tropics during rare but powerful solar events. The southern lights follow the same principles, but are harder for most people to see. Antarctica is surrounded by ocean, and few inhabited places lie beneath the southern auroral oval. Parts of southern New Zealand, Tasmania, and occasionally southern Argentina or Chile may experience auroral displays. These sightings often combine scientific research with adventure travel, as visitors journey to remote landscapes where nature remains largely undisturbed. Season also matters. Auroras are visible year-round, but darkness is essential. In polar regions, summer brings long days or even continuous daylight, making auroras impossible to see despite ongoing activity. Winter, with its extended nights, provides ideal viewing conditions. This seasonal rhythm shapes both scientific observation schedules and tourism economies, turning winter darkness into a valuable natural resource. Clear skies are equally important. Clouds can easily obscure auroras, no matter how strong the display above them. This is why regions with dry, stable winter weather are especially prized. Inland areas often experience clearer skies than coastal regions, although coastal landscapes can offer dramatic scenery when conditions align. Light pollution also plays a role. Auroras are subtle compared to artificial city lighting. Even a moderate amount of light pollution can wash out faint displays. For this reason, aurora watchers often seek remote locations far from urban centers. This has encouraged a form of slow travel where people prioritize silence, darkness, and connection to nature over speed and convenience. Interestingly, auroras are closely linked to Earth's magnetic poles, not its geographic poles. These magnetic poles slowly drift over time, reshaping the auroral ovals across decades and centuries. This movement is gradual, but measurable, and it influences long-term patterns of aurora visibility. Scientists track these changes to better understand Earth's internal dynamics and magnetic field behavior. Auroras also tend to appear more frequently around the equinoxes in March and September. While the exact reasons are complex, this seasonal pattern is thought to be related to how Earth's magnetic field interacts with the solar wind at different angles throughout the year. For observers, this means spring and autumn often bring increased aurora activity, even outside the deepest winter months. The altitude of auroras adds another layer of quiet complexity. Most auroras occur between about 80 and 300 kilometers above Earth's surface, far above airplanes and weather systems. This places them in the upper atmosphere, where space begins to blend into air. Despite being so high, auroras can appear close and immersive, creating the illusion that the lights are just beyond reach. Photographs often exaggerate aurora brightness, capturing colors that human eyes perceive more subtly. In reality, many auroras appear as pale green or whitish glows that slowly intensify. This softness contributes to their calming effect. Watching an aurora in person is less like witnessing fireworks and more like observing a slow conversation between Earth and space. Aurora visibility has shaped local culture in many polar regions. In some communities, the lights are a familiar presence rather than a rare spectacle. This familiarity has led to traditions, stories, and a sense of seasonal rhythm tied to the sky. Modern science adds explanation without diminishing the sense of quiet wonder. As you imagine these high-latitude landscapes, think of snow-covered forests, frozen lakes, and open tundra beneath a moving sky. These environments, often associated with silence and reflection, provide the perfect setting for auroras. They remind us that geography is not just about landforms, but about how Earth's position in space shapes human experience. As we drift onward, let your attention move slowly away from Earth and toward the quiet brilliance of the sun. From this vast distance, the sun does not roar or explode in constant chaos. Instead, it breathes. It exhales streams of energy so gently and continuously that most of the time we never notice. These steady outflows are known as the solar wind, and they are the first step in the long, peaceful chain of events that can eventually paint auroras across the night sky. The solar wind is made of charged particles, flowing outrons, flowing outward from the sun in all directions. This flow is not violent by default. It is a constant presence, like a cosmic breeze moving through the solar system, traveling at speeds that can exceed 1,000,000 kilometers per hour. These particles cross the space between the sun and Earth in 1 to 3 days, depending on solar conditions. The sun itself is not a solid object, but a massive sphere of hot, electrically charged gas known as plasma. Inside it, energy is produced through nuclear fusion, where hydrogen atoms combine to form helium, releasing enormous amounts of energy. Some of this energy eventually reaches Earth as light and warmth, sustaining life. Another portion escapes as magnetic and electrical activity, shaping the space environment around our planet. At times, the sun becomes more active. Dark regions known as sunspots appear on its surface, marking areas of intense magnetic activity. These regions are cooler than their surroundings, but far more dynamic. Sunspots often occur in groups and follow an approximately 11-year cycle of increasing and decreasing activity, known as the solar cycle. During periods of high solar activity, the sun may release bursts of energy called solar flares or coronal mass ejections. A solar flare is a sudden flash of radiation, while a coronal mass ejection, often called acme, is a massive cloud of charged particles launched into space. When these events are directed toward Earth, they can intensify auroral displays. Despite their dramatic names, these solar events are still part of a natural rhythm. They do not arrive with sound or visible motion across the sky. Instead, their effects unfold gradually, carried quietly across millions of kilometers of empty space. This slow journey contributes to the calm, delayed nature of auroras, which may appear hours or even days after a solar event occurs. As the solar wind approaches Earth, it encounters our planet's magnetosphere. This invisible magnetic shield surrounds Earth like a protective bubble, deflecting most charged particles away into space. Without this shield, Earth's atmosphere would be stripped away over time, as happened on Mars. The magnetosphere is generated by the movement of molten iron within Earth's core, linking deep planetary processes with cosmic phenomena. When the solar wind is mild, Earth's magnetosphere remains relatively stable. Charged particles flow smoothly around it, and auroral activity stays low. During stronger solar events, however, the magnetosphere becomes compressed and energized. Some particles are funneled along magnetic field lines toward the polar regions, where they begin their descent into the upper atmosphere. This interaction between the solar wind and Earth's magnetic field is known as space weather. Unlike terrestrial weather, it does not bring rain or wind at ground level. Instead, it influences satellites, communication systems, power grids, and navigation technologies. Modern economies and global infrastructure depend on understanding these processes, making aurora science both poetic and practical. Scientists monitor the sun, constantly using space-based observatories. Satellites like NASA's Solar Dynamics Observatory and the European Space Agency's Solar Orbiter watch the sun's surface and atmosphere in extraordinary detail. Their data helps predict solar storms and aurora activity, blending advanced technology with ancient human curiosity about the sky. The idea that the sun, so distant and constant, can influence glowing lights above Earth's poles reminds us of how connected the universe truly is. Energy released deep within the sun's core can eventually become a ribbon of green light above a snowy forest. This connection unfolds silently, without urgency, across unimaginable distances. The particles that reach Earth's atmosphere are absorbed high above us, far from where people live. Even during strong auroral events, the effects at ground level are limited. This safety allows humans to watch and enjoy auroras without fear, turning a complex physical process into a source of calm and wonder. The sun's activity also shapes auroras on other planets. Jupiter, Saturn, Uranus, and Neptune all have auroras, some far more powerful than Earth's. These extraterrestrial auroras reveal differences in magnetic fields, atmospheres, and internal dynamics, helping scientists compare planets and better understand our own. As you imagine the solar wind flowing steadily through space. Picture it not as a storm, but as a slow river of particles guided by magnetic fields and cosmic geometry. This river never stops flowing. Even on the quietest nights, it continues its journey, sometimes unseen, sometimes transforming into light. Now let your thoughts drift gently downward from the vastness of space toward the thin, fragile layers of Earth's upper atmosphere. This is where the quiet magic of auroras finally becomes visible. After traveling millions of kilometers from the sun, charged particles guided by Earth's magnetic field begin their final, delicate interaction. They do not crash violently. Instead, they meet the atmosphere in a slow exchange of energy, creating light without heat, sound, or flame. Earth's atmosphere is made of layers, each one gradually thinning as it stretches upward into space. Auroras form primarily in the thermosphere, a region that begins about 80 kilometers above the surface and extends several hundred kilometers higher. This layer is extremely thin compared to the air we breathe, yet it plays a crucial role in protecting the planet and shaping atmospheric science. As solar particles stream along magnetic field lines toward the polar regions, they collide with atoms and molecules of oxygen and nitrogen in the upper atmosphere. These collisions excite the atmospheric gases, temporarily giving them extra energy. When the atoms and molecules return to their normal state, they release that energy as light. This process is known as atomic emission, and it is the same principle used in neon signs and fluorescent lighting. The most common auroral color is green. This familiar soft green glow comes from oxygen atoms located about 100 to 300 kilometers above Earth's surface. Oxygen emits green light when it is excited and then relaxes slowly, producing a steady, calm glow that often forms broad arcs across the sky. Red auroras also come from oxygen, but from much higher altitudes, sometimes above 300 kilometers. At these heights, the atmosphere is even thinner, allowing oxygen atoms to stay excited longer before releasing their energy. The result is a deeper, quieter red light that often appears during strong solar activity, spreading gently across the sky like a distant sunrise. Nitrogen adds more subtle colors to auroras. When nitrogen molecules are excited, they can produce blue, violet, and purplish-red hues. These colors usually appear at lower altitudes, closer to 80 or 90 kilometers above the surface. Because these emissions fade quickly, nitrogen-based colors often show up as flickering edges or fine details within auroral curtains. The combination of oxygen and nitrogen emissions creates the layered, textured appearance of auroras. Greens blend into reds, purples shimmer at the edges. Blues appear briefly and vanish. Each color tells a quiet story about altitude, energy, and atmospheric composition, turning the sky into a slow-moving, scientific illustration. Auroras often take the shape of arcs, curtains, spirals, or rays. These forms are shaped by Earth's magnetic field lines, which guide charged particles in long, looping paths. The curtains appear rippled because particles are entering the atmosphere along slightly different magnetic pathways, creating parallel strands of light that move together like fabric in a gentle breeze. Despite how dynamic auroras look, the movement you see is not fast in a human sense. Changes unfold over seconds or minutes, not milliseconds. This slow pace is one reason auroras feel calming rather than dramatic. The sky seems to breathe, stretching and folding without urgency. Auroral brightness depends on both solar activity and atmospheric conditions. Strong solar storms deliver more particles, increasing intensity. Clear, dark skies allow faint auroras to be seen more easily, which is why aurora tourism thrives in remote, low-light regions. Places with minimal light pollution offer a luxury of darkness where even subtle auroras become visible. This natural connection between atmospheric science and tourism has shaped local economies in high-latitude regions. Northern Norway, Iceland, Finland, Sweden, Canada, and Alaska have built sustainable travel industries around aurora viewing. Visitors travel long distances for the chance to witness these lights, blending education, nature, and cultural experience. Many cultures have long associated auroras with meaning and storytelling. Indigenous peoples across the Arctic developed interpretations that reflected respect, caution, or reverence. Today, science provides detailed explanations, yet the emotional response remains unchanged. Understanding how auroras form does not remove their mystery. Instead, it deepens appreciation. Auroras are silent. No matter how bright or fast-moving they appear, they make no sound. The light is produced high above the atmosphere, where sound cannot travel. This silence enhances their dreamlike quality, allowing viewers to stand quietly, often in cold air, listening only to wind, snow, or their own breathing. The energy involved in auroral light production is surprisingly gentle. While the particles are energetic on an atomic scale, they carry very little total heat. If you could stand directly beneath an aurora, you would not feel warmth from it. The light exists without temperature, without touch. This gentle transformation of energy into color is one of the most peaceful processes in nature. Nothing is consumed, nothing is damaged. Energy simply changes form, then fades. It is a reminder that not all powerful forces are loud or destructive. Some of the universe's most beautiful phenomena arise from balance and flow. As you imagine these glowing curtains forming high above Earth, picture the atmosphere responding softly to incoming energy, like a musical instrument resonating quietly when touched. In the next part, we'll explore where on Earth auroras are most often seen, and why certain regions are especially favored by these lights. For now, let the colors settle in your mind. Soft greens, gentle reds, hints of violet, moving slowly, silently, above a sleeping world. As the colors from the upper atmosphere slowly fade from your thoughts, let us drift gently across the surface of the Earth. Auroras do not appear randomly across the globe. Instead, they favor specific regions shaped by Earth's magnetic field and its quiet, constant interaction with the sun. These favored regions form what scientists call the auroral zones, broad rings encircling the planet near the magnetic poles. Earth has two auroral zones, one in the northern hemisphere and one in the southern hemisphere. They are centered not exactly on the geographic poles, but on the magnetic poles, which slowly wander over time. This difference explains why auroras are more common in some countries than others, even at similar latitudes. In the north, the auroral zone passes through northern Norway, Sweden, Finland, Iceland, parts of Russia, Canada, and Alaska. These regions sit beneath the most frequent paths of incoming charged particles, making aurora sightings more reliable and more vivid. In the south, the auroral zone crosses Antarctica and the surrounding Southern Ocean, where auroras are just as beautiful but far less often seen by people. The reason auroras prefer these zones lies in Earth's magnetic field geometry. Magnetic field lines curve outward from the planet near the equator and loop back toward the surface near the poles. Charged particles from the solar wind follow these lines like invisible highways, funneling energy into narrow regions near the magnetic poles. This funneling effect creates oval-shaped regions around each pole, known as auroral ovals. Within these ovals, auroras can occur on many nights, especially during periods of increased solar activity. When the sun is quiet, the ovals contract toward the poles. When solar activity increases, they expand, allowing auroras to be seen farther south or north than usual. This expansion is why auroras sometimes appear in unexpected places. During strong solar storms, people have reported auroras as far south as the northern United States, southern Europe, and even parts of Asia. These rare events often become cultural memories, recorded in newspapers, diaries, and historical documents. Auroral visibility depends not only on location, but also on darkness. This is why winter months in high-latitude regions are ideal for aurora viewing. Long nights provide extended periods of darkness, while snow-covered landscapes reflect faint light, enhancing the visual experience. Tourism industries in these regions often combine aurora watching with luxury lodges, guided tours, and educational experiences. Places like Tromsø in Norway, Fairbanks in Alaska, and Rovaniemi in Finland have become global destinations for aurora tourism. Visitors travel for the chance to stand under a glowing sky, often pairing the experience with cultural learning, local cuisine, and quiet nature exploration. This blend of science, travel, and tranquility aligns naturally with sustainable tourism values. In contrast, regions closer to the equator rarely see auroras. Here, magnetic field lines are oriented differently, preventing solar particles from entering the atmosphere easily. Even during powerful solar storms, equatorial auroras are extremely rare and usually faint. The southern hemisphere aurora, known as the Aurora australis, mirrors its northern counterpart in physics and beauty. However, because much of the southern auroral zone lies over ocean and Antarctica, fewer people witness it. Scientists, researchers, and a small number of travelers experience these lights from ships or research stations, often describing them as equally mesmerizing. Modern technology has helped expand access to aurora viewing. Satellite imagery allows scientists to track auroral activity in real time, while space weather forecasts help travelers plan their nights. Mobile apps now offer aurora alerts, blending atmospheric science with everyday technology and education. Despite these tools, auroras remain unpredictable. Clear skies, solar activity, and magnetic conditions must align. This uncertainty adds to their appeal. The experience cannot be fully controlled or scheduled, making it feel like a quiet gift from nature rather than a guaranteed attraction. Auroras also interact subtly with Earth's rotation. Because the planet spins beneath the auroral oval, different locations pass in and out of active regions throughout the night. This movement explains why auroras often brighten and fade in cycles, rather than remaining constant. Local geography plays a role as well. Mountains, coastlines, and open plains affect viewing conditions. Coastal areas may have cloud cover, while inland regions often provide clearer skies. Many of the world's best aurora locations are far from large cities, offering dark skies and a sense of peaceful isolation. This connection between auroras and geography highlights how Earth's systems are interconnected. Space weather, magnetic fields, atmospheric chemistry, and human experience all intersect quietly above the planet's surface. Auroras are not just lights in the sky. They are the visible edge of a global system linking Earth to the Sun. As you imagine standing beneath one of these auroral ovals, picture the planet gently turning, carrying you beneath a flowing ribbon of light. In the next part, we'll explore how auroras change over time, following cycles driven by the sun itself. For now, let the idea of Earth's magnetic embrace settle softly in your thoughts. As the imagined glow of the auroral zones lingers, we now turn gently toward the sun itself. Auroras, though they dance above Earth's atmosphere, begin their story far away on the surface of our star. The sun is not constant in its behavior. Instead, it moves through slow, repeating patterns of activity known as solar cycles. And these rhythms quietly shape how often auroras appear in our skies. A solar cycle lasts, on average, about 11 years. During this time, the sun transitions from a period of relative calm to a phase of heightened activity, and then slowly back again. Scientists track this cycle by counting sunspots, which are darker, cooler regions on the sun's surface associated with strong magnetic fields. When sunspot numbers are low, the sun is considered quiet. Solar winds are steadier, and large eruptions are less frequent. During these times, auroras still occur, but they are often weaker and more tightly confined to the polar regions. As the cycle progresses toward its maximum, sunspots become more numerous. The sun's magnetic field grows more complex, twisted, and energetic. This is when solar flares and coronal mass ejections become more common, releasing vast amounts of charged particles into space. These energetic outbursts are what fuel the most dramatic auroras. When a coronal mass ejection is directed toward Earth, it can significantly disturb our planet's magnetosphere. The auroral ovals expand, intensify, and brighten, sometimes producing vivid colors and rapid motion across the sky. Solar maximum periods are especially exciting for aurora watchers. During these years, auroras are not only more frequent, but also more visible at lower latitudes. Regions that rarely experience auroras may suddenly find their night skies glowing in soft greens and reds. Historical records reveal this pattern clearly. Some of the most widely observed auroral events occurred during strong solar maximum phases. In the 19th century, during an intense solar storm known as the Carrington event, auroras were seen near the equator. Telegraph systems malfunctioned, and newspapers described skies glowing bright enough to read by at night. Despite these dramatic moments, solar cycles are generally gentle in their progression. The increase and decrease in activity unfolds gradually over years, not days. This slow rhythm contributes to the calming nature of aurora study, aligning naturally with long-term observation and patient science. Modern space agencies monitor the sun continuously. Satellites, such as those operated by NASA and ESA, observe sunspots, solar flares, and the solar wind in real time. This data helps scientists forecast space weather and predict when auroral activity may increase. These forecasts are valuable not only for aurora enthusiasts, but also for global technology. Strong solar storms can affect satellites, GPS systems, power grids, and communication networks. Understanding the sun's cycles supports infrastructure resilience and technological planning worldwide. From a human perspective, solar cycles influence tourism patterns. During solar maximum years, interest in aurora travel rises. Hotels, tour operators, and educational centers in high-latitude regions often see increased demand. Blending science, education with sustainable travel and cultural exchange. Even during solar minimum, auroras remain quietly present. They may be fainter, slower, and less dramatic, but they still appear regularly within the auroral zones. Many experienced observers appreciate these subtle displays, finding beauty in their gentler motion and softer light. Solar cycles also shape auroral colors. During high activity, increased energy allows oxygen and nitrogen atoms to emit rarer hues, including deep reds and purples. During quieter times, green auroras dominate, produced at lower altitudes where energy levels are more moderate. The sun's rhythm reminds us that auroras are not random events. They follow a cosmic heartbeat, pulsing slowly across decades. This connection between star and planet adds depth to the experience of watching the northern or southern lights. For cultures living beneath auroral skies, these cycles become part of generational memory. Elders recall especially bright years, while children grow up during quieter phases, each experiencing the same sky in different ways. This shared, yet changing phenomena strengthens the cultural significance of auroras. As you rest with this idea, imagine the sun quietly turning, its magnetic fields winding and unwinding over years. Each phase brings a slightly different sky, yet all are part of the same gentle pattern. As the quiet rhythm of the sun fades gently into the background, we now shift our awareness to perspective. Auroras are among the few natural phenomena that can be experienced, both from the ground and from far above Earth's atmosphere. Each viewpoint reveals something different, and together they form a fuller, calmer understanding of how these lights truly behave. From the surface of Earth, auroras appear as luminous curtains, arcs, and soft waves of color stretching across the night sky. To a human observer standing beneath them, the lights feel immense and immersive. They can seem close enough to touch, even though they occur more than 100 kilometers above the ground. At ground level, the experience of watching auroras is deeply personal. The stillness of cold air, the darkness of long nights, and the gentle movement of light combine into something almost meditative. Many people describe feeling small in the best possible way, aware of their place within a vast natural system. Colors seen from the ground depend on altitude and atmospheric conditions. Green is the most common hue, produced by oxygen atoms, roughly 100 kilometers above Earth. Red auroras, which form higher up, appear more diffuse and often glow softly at the edges of the display. Purple and blue tones, created by nitrogen, flicker quickly near the lower borders. The human eye also plays a role. In low light, our vision is more sensitive to motion and contrast than to color. This means auroras may appear paler in person than in photographs, which capture longer exposures. Still, the real experience carries a quiet depth that images cannot fully replicate. From airplanes flying at high latitudes, auroras can sometimes be seen from above clouds. These moments remind us that auroras occupy a layer of space just above our atmosphere, bridging Earth and the cosmos. Now, imagine viewing auroras from space itself. Satellites and astronauts aboard the International Space Station observe auroras from above, where they appear as glowing rings encircling the polar regions. From this vantage point, auroras reveal their true structure. Seen from orbit, auroras form oval shaped bands known as auroral ovals. These rings expand and contract with solar activity, shifting closer to or farther from the poles. The symmetry of these shapes reflects the structure of Earth's magnetic field, which channels solar particles toward these regions. Photographs taken from space show auroras as luminous green and red halos against the dark curve of Earth. City lights sparkle below, and clouds drift silently beneath the glowing arcs. Space-based instruments also detect auroras beyond visible light. Ultraviolet and infrared sensors capture emissions invisible to human eyes, revealing additional layers of energy transfer. These measurements help scientists understand how much energy enters Earth's upper atmosphere during solar storms. Unlike ground observers, satellites can watch auroras continuously, day and night. This constant monitoring allows researchers to map auroral activity over time, identifying patterns and responses to changes in the solar wind. Such data supports education, climate research, and global communication systems. There is a gentle poetry in knowing that while someone stands quietly beneath an aurora, a satellite passes overhead, recording the same event from a completely different angle. Both perspectives are equally valid, equally meaningful. Auroras also appear on other planets, and space exploration has expanded our understanding even further. Jupiter and Saturn, with their powerful magnetic fields, host immense auroras far larger than Earth's. These displays are driven not only by the Sun, but also by interactions with their moons. Even Mars, with its weak magnetic field, shows localized auroral events. These are detected by orbiting spacecraft rather than seen from the surface. Such discoveries remind us that auroras are a universal phenomenon, shaped by magnetic fields throughout the solar system. From a cultural and educational standpoint, these multiple perspectives enrich our appreciation of auroras. Museums, planetariums, and science centers often display satellite imagery alongside ground photography, helping visitors connect personal experience with scientific observation. Tourism industries also benefit from this layered understanding. Visitors who learn about auroras through scientific storytelling often feel a deeper connection when they finally see them in person. Knowledge enhances wonder rather than diminishing it. As you rest with this idea, imagine the aurora both above and around you. From the ground, it glides quietly overhead. From space, it forms a glowing crown around the planet. Both views are true, and both are part of the same peaceful system. As the soft image of auroras seen from Earth and space slowly fades into stillness, we now turn our attention to time. Auroras are not only shaped by space, weather, and magnetic fields, but also by the steady rhythm of Earth's seasons. The way our planet tilts, turns, and moves around the sun quietly determines when and where these lights are most often seen. Auroras can occur at any time of year. The solar wind does not pause for seasons, and charged particles constantly flow toward Earth. Yet, human visibility of auroras depends strongly on darkness. This is why winter becomes the most celebrated season for aurora viewing across the world. In polar regions, winter brings long nights that stretch for many hours. In some places, the sun does not rise at all for weeks or months. This extended darkness creates ideal conditions for watching faint celestial phenomena, including auroras. Without sunlight to wash out the sky, even subtle glows become visible. Autumn and spring are also important seasons for auroral activity. Around the equinoxes, Earth's magnetic field aligns in a way that makes it slightly easier for solar wind energy to enter the magnetosphere. This effect, sometimes called the equinoxial effect, increases the likelihood of strong auroral displays. During summer, auroras still occur, but they are often hidden by daylight. In regions near the Arctic Circle, the sun may remain above the horizon all night, creating the phenomenon known as the midnight sun. Under these conditions, auroras are present but invisible to the human eye. This seasonal dance reminds us that auroras are always there, whether we see them or not. They continue to shimmer quietly above the atmosphere, waiting for darkness to reveal them. Temperature itself does not cause auroras, but cold weather often accompanies clear skies. In many aurora viewing destinations, winter air is dry and stable, reducing cloud cover. Clear skies allow light from the aurora to travel uninterrupted to the observer. Snow-covered landscapes also enhance the experience. White ground reflects faint light upward, gently illuminating the surroundings. This creates a soft, immersive environment that feels almost dreamlike. Forests, mountains, and frozen lakes become part of the visual story. In places like northern Norway, Sweden, Finland, Iceland, Canada, and Alaska, winter tourism centers around aurora viewing. These regions combine natural beauty, cultural heritage, and modern hospitality. Glass igloos, cozy lodges, and guided night excursions offer comfort alongside scientific wonder. For many travelers, the journey itself becomes meaningful. Traveling to remote northern regions encourages slower pacing, reflection, and connection with nature. This aligns naturally with wellness, tourism, and mindful travel trends. Blending education, relaxation, and cultural exploration. The timing of auroras within a night also follows subtle patterns. Displays often intensify around local magnetic midnight, which does not always align with clock time. This moment occurs when a location faces directly away from the sun, allowing magnetic activity to concentrate overhead. Auroras may begin as faint arcs near the horizon, gradually brightening and expanding. Sudden bursts of motion, known as substorms, can cause the lights to ripple, twist, and surge. These changes may last minutes or hours, creating a gentle unpredictability. Despite these patterns, auroras remain famously elusive. Some nights offer vibrant displays, while others remain quiet. This uncertainty encourages patience and presence. Watching the sky becomes an act of stillness rather than expectation. Historically, seasonal auroras influenced human storytelling. In northern cultures, winter skies became canvases for myth and meaning. The lights were seen as spirits, omens, or pathways between worlds. These interpretations reflect humanity's long relationship with the night sky. Modern science does not erase this sense of wonder. Instead, it adds depth. Knowing that auroras arise from interactions between the sun and earth enhances appreciation. Each glowing arc becomes a visible trace of cosmic energy at work. Seasonal cycles also affect scientific research. Winter darkness allows ground-based observatories to collect clearer data. Long nights enable extended measurements of auroral behavior, contributing to space weather, forecasting, and atmospheric science. Auroras, in turn, influence Earth's upper atmosphere. Energy deposited during auroral events heats and expands the thermosphere. This can affect satellite orbits and communication systems, linking seasonal auroras to modern technology and global infrastructure. There is something soothing in recognizing these cycles. Just as days follow nights and seasons follow one another, auroras respond to rhythms far larger than ourselves. They remind us that even dramatic beauty unfolds according to quiet rules. As you rest with this idea, imagine winter skies slowly darkening, stars appearing one by one, and the first faint glow of an aurora rising above the horizon. There is no rush. The light arrives when it is ready. As we continue drifting beneath these calm polar skies, we now turn our attention to color. One of the most captivating features of auroras is their shifting palette of greens, reds, purples, and blues. These colors are not random. They are a gentle language spoken by atoms, altitude, and energy, written softly across the upper atmosphere. The most common auroral color is green. This familiar emerald glow is often the first shade people notice when they witness the northern lights for the very first time. Green auroras are produced when charged particles from the sun collide with oxygen atoms at altitudes of about 100 to 300 kilometers above Earth's surface. Oxygen is abundant in Earth's upper atmosphere, and at these heights, it responds slowly to energy. When excited by incoming electrons, oxygen releases light at a wavelength that appears green to the human eye. Because this reaction is efficient and frequent, green auroras dominate most displays. Red auroras also come from oxygen, but at much higher altitudes, often above 200 kilometers. Here, the air is thinner, and excited oxygen atoms take longer to release their energy. This delayed response produces deep red light. Red auroras are usually faint and subtle, appearing as soft glows or distant curtains rather than bright dancing shapes. Sometimes, during strong geomagnetic storms, red auroras can stretch across large portions of the sky. These rare events are especially prized by aurora watchers and photographers as they create a tranquil, almost surreal atmosphere. Blue and purple auroras originate from nitrogen. When solar particles collide with nitrogen molecules or ions, they emit shorter wavelengths of light. Blue auroras tend to appear at lower altitudes, often beneath green arcs, forming a layered effect. Purple and violet hues can appear where blue nitrogen light mixes with red oxygen emissions. Pink auroras, often seen along the lower edges of auroral curtains, are the result of blended colors. When green oxygen light overlaps with red or blue nitrogen emissions, the colors merge into soft pink tones. These mixed hues add complexity and depth to the display. The altitude of the aurora plays a key role in determining its color. Lower altitude auroras are denser and more energetic, producing brighter, sharper colors. Higher altitude auroras are fainter and smoother, creating gentle washes of light. Human vision also influences how we perceive aurora colors. In low light, our eyes rely more on rod cells, which are sensitive to brightness but less sensitive to color. This means faint auroras may appear gray or white to the naked eye, even though cameras reveal vivid colors. Long exposure photography captures auroras differently. By collecting light over several seconds, cameras reveal details and colors that human vision may miss. This has contributed to the popularity of aurora tourism and travel photography, blending science, art, and luxury experiences. Modern technology allows travelers to document auroras with smartphones and professional equipment alike. This intersection of nature and technology highlights how ancient phenomena continue to inspire modern creativity and digital storytelling. Despite advances in imaging, seeing auroras with the naked eye remains a deeply personal experience. The colors appear softer, more fluid, and more alive. They do not feel static, but responsive, as if the sky itself is breathing. Scientists study auroral colors to understand space weather conditions. Different colors reveal information about particle energy, atmospheric composition, and magnetic interactions. By analyzing light spectra, researchers can measure what happens far above Earth's surface. Auroral colors also vary by latitude. Near the poles, green and red dominate, while lower latitudes may see more red during intense solar storms. These rare low-latitude auroras have been recorded throughout history, often surprising communities unaccustomed to seeing lights in the sky. Historical records describe red skies during major solar events, sometimes mistaken for distant fires or omens. Today, these accounts help scientists reconstruct past solar activity, linking human history with cosmic cycles. Cultural interpretations of auroral colors vary across the world. In some traditions, green auroras symbolized prosperity or renewal. Red auroras were sometimes associated with warnings or transitions. These stories reflect humanity's instinct to find meaning in color and light. From a calming perspective, auroral colors have a soothing psychological effect. Soft greens and blues are often associated with relaxation, nature, and balance. This makes aurora-themed content ideal for sleep, meditation, and mindful listening. In wellness-focused travel, aurora viewing is often paired with quiet activities like thermal bathing, forest walks, and stargazing. These experiences encourage slow living and connection with the natural world, supporting mental well-being and rest. The science of auroras reminds us that color itself is a form of information. Light carries messages across vast distances, from the sun to earth, from atoms to our eyes. Each hue tells a story of energy, motion, and interaction. As you imagine these colors drifting overhead, there is no need to label or analyze them further. Simply let them exist. Green fades into blue, blue into purple, purple into soft darkness. The transitions are gentle, without sharp edges. Auroras do not rush. They unfold at their own pace, responding to invisible forces. Watching them teaches patience, presence, and quiet curiosity. As we continue this gentle journey beneath polar skies, we now drift closer to Earth itself, to the invisible layers of air that protect and surround our planet. Auroras are not only a spectacle of space, they are also a quiet conversation between the sun and Earth's atmosphere, unfolding far above where clouds form and birds fly. Earth's atmosphere is layered like a soft blanket. Closest to the ground is the troposphere, where weather, rivers of wind, and daily life unfold. Above it lies the stratosphere, home to the ozone layer, where Earth's atmosphere slowly fades into space. Auroras occur primarily in the thermosphere, a region that begins around 80 kilometers above Earth's surface and extends hundreds of kilometers outward. Despite its name, the thermosphere is extremely thin. The air is so sparse that it would feel like a near vacuum to humans. Yet it plays a crucial role in space science and satellite travel. When charged particles from the sun follow Earth's magnetic field lines toward the poles, they enter the thermosphere and collide with gases like oxygen and nitrogen. These collisions excite the atoms and molecules, causing them to release light. This is the moment when auroras are born. The thermosphere expands and contracts depending on solar activity. During periods of high solar energy, it can swell outward, increasing atmospheric drag on satellites. This subtle expansion is one reason why space agencies carefully monitor auroral activity and space weather. Auroras are part of a broader system known as space weather. Just as Earth has weather patterns shaped by oceans and air currents, space has weather driven by the sun's activity. Solar flares, coronal mass ejections, and fast solar winds can all influence auroral intensity. Most of the time, space weather is gentle and manageable. Auroras glow quietly above the poles, unseen by most of the world. But during strong solar storms, auroras can become brighter, larger, and more widespread, reaching lower latitudes. These powerful events can also affect modern technology. Satellite communications, GPS navigation, aviation routes, and power grids can all be influenced by intense geomagnetic storms. This makes auroras not only beautiful, but also important indicators of space conditions. Airlines sometimes adjust polar flight routes during strong auroral activity to reduce radiation exposure and communication disruptions. In this way, auroras quietly shape global travel and aviation logistics, linking natural phenomena to the modern economy. Despite these effects, auroras themselves are harmless to people on the ground. Earth's atmosphere and magnetic field provide strong protection from harmful solar radiation. The light we see is the safe, visible expression of much larger forces at work. The atmosphere also influences the shape of auroras. Curtains, arcs, rays, and spirals form as particles travel along magnetic field lines and interact with varying atmospheric densities. These structures shift and ripple, responding to subtle changes in energy and direction. Auroral arcs often stretch east to west, following lines of constant magnetic latitude. They can remain stable for minutes or hours, creating a sense of stillness. Then, without warning, they may break into motion, dancing and folding like slow-moving fabric. This movement is not random. It reflects changes in Earth's magnetosphere, the region dominated by our planet's magnetic field. When energy builds up and releases, auroras respond, brightening and accelerating. Scientists use ground-based cameras, satellites, and radar systems to study these interactions. By observing auroras, researchers gain insight into how Earth's atmosphere exchanges energy with space. Auroras also help scientists understand atmospheric chemistry. The light emissions reveal how gases behave under extreme conditions, offering clues about processes that cannot be easily recreated in laboratories. Beyond Earth, auroras have been observed on other planets. Jupiter, Saturn, Uranus, and Neptune all have auroras, shaped by their own magnetic fields and atmospheres. Studying Earth's auroras helps scientists interpret these distant worlds. Auroras are powered not only by the sun, but also by volcanic material from its moon, Io. This shows how atmospheric and magnetic interactions can vary across the solar system. Back on Earth, auroras remain deeply tied to place. They are most often seen in high-latitude regions where the atmosphere and magnetic field align favorably. This has shaped settlement patterns, tourism industries, and cultural identities in polar regions. In places like northern Norway, Iceland, Canada, and Finland, aurora tourism supports local economies. Travelers seek quiet nights, dark skies, and moments of stillness beneath glowing curtains of light. These destinations often emphasize sustainability and respect for nature, blending scientific education with cultural storytelling. Visitors learn not only how auroras form, but also how communities have lived with them for generations. From a sleep-friendly perspective, auroras remind us that even powerful forces can express themselves gently. Immense energy from the sun arrives at Earth and transforms into soft light, moving slowly across the sky. This transformation mirrors the way our own thoughts can soften as we rest. Activity gives way to calm. Complexity becomes simplicity. As you imagine Earth wrapped in its atmospheric layers, protected and balanced, there is a sense of reassurance. The planet quietly manages vast energies, maintaining harmony between space and surface. Long before satellites, space stations, or scientific instruments, humans looked up at the night sky with quiet curiosity. When auroras appeared, glowing softly or blazing brightly across the darkness, they left deep impressions on those who witnessed them. This part of our journey drifts gently through history, exploring how different cultures understood the northern lights long before modern science offered explanations. Auroras have been observed for thousands of years. Texts dating back more than 2,000 years describe strange red vapors and shimmering lights in the northern sky. These accounts were often recorded alongside celestial events like comets and eclipses, showing that auroras were considered important signs. In ancient Chinese philosophy, the sky was deeply connected to earthly order, governance, and harmony. Unusual lights in the heavens were sometimes interpreted as messages, signaling changes or imbalances. While these interpretations were symbolic rather than scientific, they show careful observation and respect for the natural world. In Europe, early Greek and Roman writers also noted strange sky glows. The philosopher Aristotle described faint lights and moving colors in the northern sky, though he believed they were atmospheric phenomena similar to glowing clouds. The Roman naturalist Pliny the Elder wrote of sky fires that sometimes appeared at night. These early descriptions are valuable today. Modern scientists use historical aurora records to reconstruct past solar activity. By comparing ancient observations with modern data, researchers can learn how the sun behaved centuries ago. In the far north, indigenous cultures developed rich and varied interpretations of auroras. For the Sami people of northern Scandinavia, auroras were powerful and respected. Some traditions taught that the lights were spirits of the dead, visible reminders of ancestors watching over the living. Because of this belief, people were careful when auroras appeared. Loud noises, whistling, or careless behavior were sometimes avoided out of respect. The lights were not feared, but they were taken seriously, woven into moral and social guidance. Among Inuit communities across Arctic Canada and Greenland, auroras were often seen as spirits playing games in the sky. In some stories, they played ball with a walrus skull, moving swiftly and joyfully across the heavens. These stories reflect a sense of playfulness and connection rather than fear. In other indigenous traditions, auroras were believed to guide animals, influence hunting success, or mark seasonal transitions. These interpretations were deeply tied to survival, ecology, and the rhythms of Arctic life. In medieval Europe, auroras were rarer sights due to lower solar activity and less travel to high latitudes. When they did appear, especially red auroras seen farther south, they were sometimes interpreted as omens of war, plague, or divine intervention. Historical records describe red skies glowing over cities like London, Rome, and Paris during intense geomagnetic storms. Without scientific context, these displays could be alarming, especially during times of social or political uncertainty. One famous event occurred in 1859 during the Carrington event, the most powerful geomagnetic storm ever recorded. Auroras were seen as far south as the Caribbean. Newspapers reported skies so bright that people could read at night. telegraph systems failed, operators received electric shocks, and sparks flew from equipment. This event marked a turning point, showing humanity that solar activity could directly affect technology and communication. As science advanced in the 18th and 19th centuries, auroras gradually shifted from myth to measurement. Instruments replaced superstition, though wonder remained. The term aurora borealis was popularized by Galileo Galilei in the early 1600s. He named it after Aurora, the Roman goddess of dawn, and Boreas, the Greek god of the north wind. The name itself reflects a poetic blend of myth and observation. In the southern hemisphere, auroras are known as Aurora australis. Indigenous cultures in Australia, New Zealand, and southern South America also developed interpretations of these lights, often linking them to fire, spirits, or ancestral presence. The MRE of New Zealand sometimes described the southern lights as reflections of campfires lit by ancestors who traveled south. These stories connected sky phenomena to genealogy and place. As global exploration expanded, sailors and explorers documented auroras during polar expeditions. These records contributed to growing scientific understanding and inspired generations of researchers. Auroras became symbols of the polar regions themselves, representing remoteness, beauty, and the meeting of Earth and space. They appeared in travel journals, paintings, and later, photography. In modern times, auroras have become cultural icons. They feature in tourism campaigns, art installations, documentaries, and educational content. Seeing the northern lights is often described as a once-in-a-lifetime experience. This global fascination supports local economies in high-latitude regions. Hotels, guides, transportation services, and cultural centers benefit from aurora tourism, blending science, travel, and storytelling. Yet, even as auroras become more accessible through technology, they retain an ancient quality. They cannot be controlled, scheduled, or guaranteed. They appear when conditions align, rewarding patience and stillness. From a sleep-friendly perspective, auroras invite us to slow down and observe without expectation. Ancient people watched them without knowing why they formed, yet still found meaning and beauty in their presence. Today, even with scientific explanations, that sense of quiet wonder remains. Understanding how auroras form does not diminish their impact. Instead, it adds depth, connecting physics with poetry. As you imagine ancient observers standing beneath glowing skies, wrapped in furs or cloaks, listening to the wind and watching the lights, there is a feeling of continuity. Across centuries and cultures, humans have shared this same sky. As we continue softly onward, we move from ancient stories into the quiet precision of modern science. Auroras are still just as beautiful as they were thousands of years ago. But today, they are also carefully observed, measured, and studied using technology that reaches far beyond Earth's surface. This part explores how scientists watch the northern lights today, gently blending advanced research with the same sense of wonder humans have always felt. Modern aurora science begins far above the planet, in space itself. Satellites orbiting Earth constantly monitor the sun, the solar wind, and Earth's magnetic environment. These space-based observatories act as early warning systems, allowing scientists to see solar storms days before they reach Earth. One of the most important tools is NASA's fleet of solar observation satellites. Missions such as the Solar Dynamics Observatory and the Advanced Composition Explorer measure solar flares, coronal mass ejections, and streams of charged particles. These observations help predict when auroras may intensify. When a burst of solar energy leaves the sun, it travels across space at immense speed. Satellites positioned between the sun and Earth measure its density, speed, and magnetic orientation. This information is essential for understanding how strong an auroral display might become. Closer to Earth, other satellites focus specifically on auroras. Some orbit over the poles, passing repeatedly through auroral zones. These spacecraft measure particle energy, electric currents, and magnetic disturbances directly inside the glowing regions. NASA's Themis mission, for example, was designed to study how energy from the sun is released into Earth's magnetosphere. By flying multiple spacecraft in formation, scientists can observe how auroras are triggered almost in real time. On the ground, research stations are scattered across high-latitude regions. In places like northern Norway, Alaska, Canada, Iceland, and Antarctica, scientists maintain observatories dedicated to aurora research. These locations are chosen for their proximity to the auroral oval and their relatively dark skies. Ground-based cameras capture detailed images of auroras in visible light. Some cameras are optimized to detect specific wavelengths, allowing researchers to identify which atmospheric gases are glowing at any moment. This helps determine altitude and particle energy. All sky cameras, with wide-angle lenses, record the entire sky at once. These instruments create continuous time-lapse records revealing how auroras evolve minute by minute. Watching these recordings feels almost like watching the Earth breathe. Magnetometers are another key tool. These instruments measure tiny changes in Earth's magnetic field caused by electric currents flowing during auroral activity. By analyzing magnetometer data from many locations, scientists map the structure and strength of geomagnetic storms. Radars are also used, particularly systems like the Super DAR network. These radars send radio waves into the upper atmosphere and measure how charged particles move. This reveals wind patterns, electric fields, and plasma flows linked to auroras. Together, satellites, cameras, radars, and magnetometers form a global observing system. Data from these tools is shared internationally, reflecting how aurora science crosses borders and cultures. One of the main goals of modern aurora research is space weather prediction. Auroras themselves are beautiful, but the same processes that create them can disrupt technology. Understanding auroras helps protect satellites, power grids, aviation systems, and communication networks. Airlines, for example, pay close attention to auroral activity. During strong geomagnetic storms, flights over polar regions may be rerouted to avoid increased radiation exposure and communication issues. This shows how aurora science quietly supports global travel and transportation. Power companies also monitor space weather. Strong geomagnetic currents can induce electrical flows in long transmission lines, potentially damaging transformers. By studying auroras, engineers learn how to reduce these risks. Aurora research also contributes to fundamental science. Studying how charged particles interact with magnetic fields helps scientists understand plasma physics, a field relevant to fusion energy, space exploration, and advanced technology. Even planets beyond Earth experience auroras. Spacecraft have observed auroras on Jupiter, Saturn, Uranus, and Neptune. Comparing these planetary auroras helps scientists understand magnetic fields across the solar system. Jupiter's auroras, for example, are extremely powerful and influenced not only by the solar wind, but also by volcanic material from its moon, Io. These discoveries expand Aurora science into planetary astronomy. Modern technology also allows everyday people to participate in Aurora observation. Citizen science projects invite photographers and sky watchers to submit images and reports. These contributions help fill gaps between professional observatories. Aurora alert apps and websites now provide real-time forecasts based on satellite data. People around the world check these forecasts, planning quiet nights of observation or peaceful photography sessions. This blending of science and lifestyle has created a unique connection between research and relaxation. Watching auroras has become part of wellness travel, slow tourism, and mindful experiences in nature. High-latitude destinations promote aurora watching as a calm, luxurious escape. Travelers stay in glass-roofed cabins, remote lodges, or eco-friendly hotels, combining comfort with natural wonder. For scientists working long winter nights at polar stations, auroras are both research subjects and quiet companions. Many researchers describe moments of stepping outside during observations, simply watching the sky in silence. Despite all the technology, auroras still resist full prediction. Forecasts can estimate activity levels, but the exact shapes, colors, and timing remain uncertain. This unpredictability preserves their magic. From a sleep-friendly perspective, aurora science reminds us that even in a highly technological world, nature still moves on its own schedule. The lights appear when conditions align, not when we demand them. As you imagine satellites gliding silently above Earth and researchers watching softly glowing skies below, there is a sense of balance. Science observes, measures, while the auroras continue their gentle dance. As we continue gently onward, we drift from the instruments of science to the quiet geography of the Earth itself. Auroras do not appear everywhere. They favor certain regions, shaped by latitude, magnetic fields, climate, and darkness. In this part, we explore where the northern and southern lights most often reveal themselves, and why these places feel so deeply connected to the glowing sky. Auroras form in broad rings around Earth's magnetic poles, known as auroral ovals. These ovals are not fixed lines on a map. They gently expand and contract depending on solar activity, breathing with the rhythm of the sun. Most of the time, the auroral oval sits between about 65 and 75 degrees latitude. This places it across the far northern and southern regions of the planet, where long winter nights and open skies create ideal viewing conditions. In the northern hemisphere, the aurora borealis is most commonly seen across parts of Scandinavia, northern Russia, Alaska, Canada, Greenland, and Iceland. These regions lie beneath or near the auroral oval, making auroras a frequent visitor. Northern Norway is one of the most famous aurora destinations in the world. Towns like Tromsø sit directly beneath the auroral oval, offering frequent displays during winter months. The surrounding fjords, mountains, and coastal landscapes create a calm, almost dreamlike setting. Finland's Lapland region is another well-known location. Vast forests, frozen lakes, and minimal light pollution make it ideal for quiet aurora watching. Many visitors experience the lights from cozy cabins or glass-roofed igloos designed for peaceful observation. Sweden's northern areas, especially around Abisko National Park, are famous for relatively clear skies. Abisko lies in a rain shadow created by surrounding mountains, reducing cloud cover and increasing viewing opportunities. Iceland offers a unique aurora experience. Its location near the auroral oval, combined with dramatic volcanic landscapes, waterfalls, and black sand beaches, makes aurora watching feel both powerful and serene. On quiet nights, the lights reflect off glaciers and oceans. Across the Atlantic, Alaska provides some of the most intense auroral displays in the Northern Hemisphere. Fairbanks is particularly well positioned, sitting directly under the auroral oval and far from major city lights. Canada's northern territories, including Yukon, Northwest Territories, and northern Manitoba, are also prime locations. Churchill, Manitoba, known for its polar bears, is equally famous for its auroras dancing above snowy tundra. Greenland, with its vast ice-covered landscapes and long winter nights, offers some of the darkest skies on Earth. Auroras there feel ancient and untouched, glowing above icebergs and frozen coastlines. In Russia, northern regions such as Murmansk and the Kola Peninsula experience frequent auroras. These areas combine Arctic geography with cultural history shaped by long winters and the luminous sky. Auroras can occasionally be seen farther south during strong geomagnetic storms. In such moments, the auroral oval expands, allowing people in lower latitudes to witness rare displays. Cities like London, New York, Paris, or even parts of the Mediterranean have recorded rare aurora sightings during extreme solar events. These moments are brief but unforgettable, often remembered for a lifetime. In the southern hemisphere, the aurora australis mirrors its northern counterpart. However, fewer people see it because much of the southern auroral oval lies over the ocean. Antarctica offers the most consistent aurora australis displays. Researchers stationed there often describe auroras stretching across the entire sky, glowing above ice sheets and research stations in complete silence. Southern Australia, Tasmania, New Zealand's South Island, and parts of southern South America can also experience auroras during strong activity. These locations provide rare opportunities for travelers and photographers. New Zealand's southern regions, especially around Stewart Island and Otago, are known for occasional aurora sightings. When conditions align, green and red light ripple above the Southern Ocean. Tasmania, with its dark skies and southern latitude, has become a quiet destination for aurora watchers. The experience often involves standing alone on a cold beach, listening to waves while the sky glows softly. In South America, Patagonia, and Tierra del Fuego occasionally witness auroras. These remote landscapes, shaped by wind and glaciers, echo the feeling of isolation and wonder found in polar regions. What all these places share is darkness. Auroras are faint compared to city lights, so minimal light pollution is essential. This is why aurora watching often takes place far from urban centers. Winter is the best season for auroras, not because they occur more often, but because nights are longer. In high-latitude regions, winter brings many hours of darkness, increasing viewing opportunities. Cloud cover plays a major role. Clear skies are essential, and some locations benefit from geographic features that reduce cloudiness, such as mountain ranges or dry Arctic air. Temperature does not directly affect auroras, but cold air often brings clearer skies. Many aurora destinations are cold, quiet, and still, adding to the calming atmosphere. Modern tourism has adapted to these conditions. Aurora-focused travel often emphasizes slow experiences, warm accommodations, and gentle schedules that align with nature. Travelers are encouraged to dress warmly, move slowly, and remain patient. Watching auroras is not about rushing, but about waiting quietly, often in silence. Aurora watching teaches stillness, attention, and acceptance of uncertainty. There is no guarantee of seeing the light, even in the best locations. This uncertainty encourages presence rather than expectation. When auroras do appear, they often begin faintly. A pale arc forms low on the horizon, slowly brightening. Over time, it may rise, ripple, and transform. Watching this progression feels like watching a story unfold at the pace of nature, not human schedules. As you imagine these far northern and southern places, you may picture snow-covered landscapes, frozen lakes, quiet oceans, and star-filled skies. As we move gently forward, the landscapes fade into the background, and our attention rises once more to the sky itself. In this part, we explore the colors, shapes, and movements of auroras, the visual language through which Earth and the Sun quietly communicate. Auroras are often described as green, but this is only the beginning of their palette. The colors of auroras depend on which gases in Earth's atmosphere are excited, and at what altitude those interactions occur. The most common aurora color is a soft, luminous green. This green glow comes from oxygen atoms located about 100 to 300 kilometers above Earth's surface. When charged particles from the sun collide with these oxygen atoms, energy is released as green light. Green auroras often appear bright and well-defined, making them the most visible to the human eye. This is why many first-time aurora watchers remember a gentle green curtain or arc stretching across the sky. Higher in the atmosphere, oxygen can produce red auroras. These red glows occur above 200 kilometers, where the air is thinner and collisions are less frequent. Red auroras are usually fainter and more diffuse. Red auroras often appear as soft glows at the top of green displays, or as faint red arcs on the horizon. They can feel subtle and mistaken for distant city lights or clouds. Nitrogen, another major component of Earth's atmosphere, contributes additional colors. When nitrogen molecules are excited, they can produce blue and purple hues. Blue auroras are relatively rare and tend to appear at lower altitudes where atmospheric density is higher. These displays can look electric and sharp, adding contrast to the softer greens and reds. Purple and pink auroras often appear along the edges or lower portions of green curtains. These colors emerge when nitrogen emissions blend with oxygen's green glow. Occasionally, auroras can appear white or gray to the naked eye. This happens when the light is faint and the human eye struggles to distinguish color in low light conditions. Long exposure photography often reveals colors that were not easily visible in real time. Cameras can capture deep reds, vibrant purples, and layered greens that unfold slowly across the sky. Auroras are not static lights. Their motion is one of their most captivating features. They shift, ripple, pulse, and dance in ways that feel almost alive. One common aurora shape is the arc. Arcs appear as long, curved bands of light stretching from east to west. They often mark the beginning of an auroral display. As activity increases, arcs can break into curtains. Curtains look like vertical sheets of light with fine ripples that resemble fabric moving in a breeze. These ripples form along magnetic field lines, revealing the invisible structure of Earth's magnetic environment. The sky becomes a map of forces we cannot see but can gently observe. Another aurora form is the corona. Coronas occur when auroras appear directly overhead, radiating outward in all directions. They can feel immersive, surrounding the observer completely. Pulsating auroras are another fascinating type. These auroras blink on and off rhythmically. Sometimes every few seconds. They often appear late at night or early in the morning. The pulsing effect is linked to interactions between solar particles and Earth's radiation belts, creating periodic bursts of energy that light up the atmosphere. Diffuse auroras form large, faint glows that cover wide areas of the sky. These are softer and less defined, creating a gentle ambient light rather than sharp shapes. Auroras can also form spirals, waves, and flickering rays that shoot upward like beams. These rays align with magnetic field lines, pointing directly into space. The speed of aurora motion varies. Some displays move slowly, unfolding over minutes like a calm tide. Others can change rapidly, shifting shapes in seconds. This variation depends on the intensity of geomagnetic activity and the structure of incoming solar particles. Stronger solar storms often produce faster, more dynamic auroras. Despite their movement, auroras are silent. The atmosphere at auroral altitudes is far too thin to carry sound. The experience is visual only, deepening the sense of quiet. Some cultures historically believed auroras made sounds, describing whispers, crackles, or soft hums. While modern science finds no direct sound production at auroral heights, these stories reflect the emotional impact of witnessing the lights. The human brain often fills silence with imagination, especially in unfamiliar environments. The quiet presence of auroras can feel so powerful that it invites interpretation. Aurora shapes are influenced by Earth's magnetic field geometry. This field channels charged particles along curved paths, shaping the lights into arcs and curtains. The magnetic field is not perfectly symmetrical, which is why auroras can appear uneven or lopsided across the sky. Solar wind conditions also affect shape. Changes in speed, density, or direction of the solar wind can quickly alter auroral patterns. Sometimes auroras appear as a steady glow. Other times they explode into motion, filling the sky with energy. Both states are part of the same natural process. Watching auroras teaches patience and attention. The most subtle changes often happen slowly, rewarding those who remain still and observant. This slow unfolding aligns beautifully with relaxation. Aurora watching is not about constant excitement, but about being present for gentle transformations. Many people describe auroras as calming, despite their power. The soft light, steady motion, and silence create a meditative atmosphere. From a scientific perspective, auroras are visual evidence of space weather. The interaction between the sun and Earth's magnetic shield. From a human perspective, they feel like stories written in light, moving across the sky without words. As you imagine these colors and shapes, picture them drifting slowly, breathing in and out, fading and returning. As we arrive at the final part of this journey, the sky grows calmer. The lights slow, the colors soften, and the moment invites reflection. In this closing chapter, we explore what auroras quietly teach us, not just about science, but about our relationship with Earth, space, and time itself. Auroras remind us that our planet is not isolated. Earth exists within a flowing environment shaped by the sun. Streams of energy travel millions of kilometers through space and gently touch our atmosphere, making the invisible visible. Every aurora is evidence that Earth is connected to a much larger system. The same sun that warms oceans, supports agriculture, and powers economies also sends charged particles outward, shaping space weather far beyond our planet. This connection highlights the protective role of Earth's magnetic field. Without it, solar particles would strip away the atmosphere over time, as scientists believe happened on Mars. Auroras are a sign that this shield is working. Rather than being destructive, most solar interactions are gracefully redirected. The energy is guided toward the poles where it becomes light instead of harm. Auroras also teach us about balance. They occur where opposing forces meet: solar, wind, and magnetic field, energy and protection, motion and stillness. This balance mirrors many natural systems on Earth. Rivers carve landscapes slowly. Mountains rise through steady pressure. Forests grow through quiet cycles of decay and renewal. Auroras fit into this pattern. They are dramatic, yet gentle, powerful, yet calm, brief, yet part of an ongoing process that has lasted billions of years. From a human perspective, auroras connect science and emotion. They can be measured, modeled, and predicted, yet they also inspire awe that transcends data. Scientists study auroras using satellites, ground stations, and advanced computer models. These tools help improve space weather forecasting, which protects satellites, power grids, aviation, and global communication systems. Modern economies depend on technologies vulnerable to solar storms. Auroras are a visible reminder of why understanding space weather matters for travel, technology, and infrastructure. Airlines adjust flight paths during strong geomagnetic storms to reduce radiation exposure and maintain communication. Satellites are placed into safe modes. Power companies monitor electrical grids. Auroras, while peaceful to watch, signal dynamic processes that modern society must respect and prepare for. At the same time, auroras continue to inspire tourism. Northern destinations like Iceland, Norway, Finland, Canada, and Alaska welcome travelers seeking quiet nights under glowing skies. Aurora tourism blends science, nature, and luxury travel. Visitors stay in glass-roofed lodges, remote cabins, or eco-friendly resorts designed to minimize light pollution. These experiences often emphasize sustainability, reminding travelers to respect fragile Arctic environments while enjoying their beauty. Auroras also connect cultures across generations. Indigenous stories, medieval chronicles, and modern photography all reflect humanity's desire to understand the sky. Even today, many first-time viewers feel a sense of humility beneath the lights. The sky feels larger, time feels slower. Auroras encourage stillness. They ask nothing from us except attention. In a world of constant movement, notifications, and noise, auroras offer a rare invitation to pause, to look up, to wait. They cannot be rushed. Schedule guarantees their appearance. This unpredictability teaches patience and acceptance. And that, too, is part of the experience. Auroras remind us that not all beauty is controllable or repeatable. Some moments exist only once, unrecorded, living briefly in memory. This makes them especially meaningful. From a scientific standpoint, auroras will continue as long as the sun shines and Earth's magnetic field endures. From a human standpoint, they will continue to inspire stories, curiosity, and calm for generations to come. As you imagine the sky now, picture it dark and vast. A faint glow appears on the horizon. It grows slowly, then drifts upward, forming a soft arc. The arc becomes a curtain. The curtain ripples gently, like breath moving through fabric. Colors shift subtly green, then a hint of red, then back to green again. The motion slows, the light fades, the sky returns to stillness. And yet, nothing has ended. The process continues invisibly, patiently, waiting for the next moment to glow. As you rest, remember that above you, even now, Earth and Sun are quietly exchanging energy. You are part of that system, safe beneath the magnetic shield, connected to a universe that moves with calm persistence. Let that thought settle gently. This concludes our journey through the quiet science of auroras. May the calm of the northern light stay with you, drifting softly into rest.